Hi, this is going to be a discussion of polyprotic acids. There are going to be two parts to this discussion. The first part, we'll talk about writing the dissociation equations. And the second one will be involved with how we calculate concentrations at equilibrium for polyprotic acids. So let's bring up an example here. So in this example, it says that sulfurous acid, H2SO3, is a polyprotic acid. And we want to write the balanced equations, notice it says equations 2, for the sequence of reactions that sulfurous acid can undergo when it's dissolved in water. So notice that the H2SO3 actually has two hydrogens at the beginning there, right here, right? So we're going to have two equations. If it had three hydrogens, we would have three equations. Okay, this is an acid. It's a weak acid. Sulfurous acid is a weak acid. Don't get it confused with sulfuric acid, H2SO4, which is a strong acid. Okay. Let's take a look. All right, so what we're going to do is we're going to start with the chemical formula of the acid. So here's H2SO3. And we're going to dissolve it into water. So we write it as aqueous, right? Then the first step is, in Alex, it's going to just show you a regular arrow, but since it's a weak acid, we would typically write a double arrow, but they may just want you to write the individual arrow. And what we do is we just essentially take the H plus off and dissociate it from the acid. So the acid gives off an H plus, okay? The next step is, well, what's left over? Well, if we take off one hydrogen, that means we just have one left. But we're not getting rid of a hydrogen atom, we're getting rid of a hydrogen ion. So we lose a plus charge, so it's now negatively charged. And again, it's dissolved in water, okay? So that's one way to write it. And then the second step would be, this is now the conjugate acid, I'm sorry, the conjugate base of this sulfurous acid. But because it's a polyprotic acid, what that means is more than one proton can be removed. So now we're going to do the second equation, which is just going to give us the second hydrogen. And so look what happens. You get an extra hydrogen. Okay. Now, again, they're weak acids, so you're not going to get 100% ionization off of this. You might only get maybe 1% or 0.1% or even 0.01% for that H plus in the first equation. For the second equation, it's even less. When you have a polyprotic acid, the second hydrogen is much weaker than the first one. Now, we could also write this, if we wanted to, as a Bronsted-Lowry acid. And in that case, what we would do is we would react it with water, right? That's how we do Bronsted-Lowry. This is really Arrhenius up here. This is an Arrhenius acid. So we react it, the H plus is donated to the water. So now you get HSO3 minus. But now the water has an extra H plus, so now we get the hydronium ion. And likewise, with the second equation, we would do the same thing. We'd take our conjugate base over here, but because this was a polyprotic acid, the conjugate base is actually going to behave like an acid if you put it into water. So it's a weak acid, very weak. The second one will be very weak acid, but it will donate an H plus to some of the water molecules in the solution. So you get your other hydrogen. Okay, so there you go. So there's two ways to do it. In the Alex, I think they want you to do it the first way, but you can check on that just to make sure. We can either do dissociation or we can do Bronsted-Lowry acids, okay, acid-base chemistry. Let's look at another example. Now this one is for oxalic acid, H2C2O4. It's a polyprotic acid, right? The balanced chemical equations for the sequences of reactions that oxalic acid can undergo when it's dissolved in water. Again, this is essentially the same kind of idea. This is H2C2O4, and we're going to put it into water. So you're going to get H plus. That's what an acid does, right? One way of looking at it is that acids in general will give off an H plus if you put them into water. And then we take one of the hydrogens off. So now we still have one C2O4, but we gave off an H plus. So we have to have a negative over here, right? So there's your first ionization. Written with the second one, we take the product. All right, so you take this product right here, that becomes the reactant. So now it forms another H plus. And you get rid of another hydrogen. So now it becomes 2 negative, right? If you lose another H plus, now it becomes -2. Every time you lose an H plus, the counter ion, the conjugate base, becomes negative by 1 more. Okay. We can write this if we want to as a reaction with water. So we add water to it. H plus goes to the water. So you get HC2O4. Notice in doing it as a Bronsted-Lowry acid, you get the same conjugate base as if you did it just as a dissociation. So now you have an extra H plus, so it's hydronium, right? And then this again becomes the reactant. React it with another one. H plus goes over here, you get C2O4, 2 minus, and hydronium. Okay, again, the second one is going to be a weaker acid than the first one. So, typically what they do is they'll say, hey, there's a Ka1 here, meaning this is the first acid dissociation constant. And then there's another one here, so we call that Ka2. And in general, Ka2 is much lower, much smaller than Ka1. It's much weaker, usually by thousands or tens of thousands smaller. So this is a weak acid, but this is a very weak acid. Okay, the second one is going to be weaker than the first. So stay tuned for part 2. What we'll do is we'll look at some calculations now involving these polyprotic acids.